Okay, it's our pleasure to introduce the second speaker, James Walsh. He is a common postdoctoral fellow at the Cornell University. His research is in mathematical logic and proof theory. He received his PhD from the group in logic at the UC Berkeley and received the 2020 Sachs Prize from the Association for Symbolic Logic for the most outstanding dissertation in mathematical logic worldwide. Okay, and today he will talk about the hierarchy of natural theories. Okay, please.
Okay, well, thank you for the introduction, and thanks for inviting me here to speak, and thanks to all of you for coming today. So the starting points for today's talk are the incompleteness theorems, also the topic of the workshop. So the first theorem says that no reasonable Gödelian axiomatic theory is complete, and the second says that no Gödelian axiomatic theory proves its own consistency. And I'll just leave it to you to fill in what Gödelian means here. But the first theorem says that there is no universal axiomatic framework for developing arithmetic. Instead, we're left with this vast array of ever stronger axiom systems. And the second theorem gives us one of the primary means of measuring and comparing the relative strength of axiom systems. And that's the notion of consistency strength. So I'm going to recall what this notion is. So if we pick a suitable base theory B, we can say that T has smaller consistency strength than U, modulo B, if B proves that the consistency of U implies the consistency of T. Now, often we'll just pretend that we've chosen a suitable B and chosen a suitable B and suppress mention of B. We'll say that T has a strictly smaller consistency strength than U if T is as weak as U, but U is not as weak as T. And we'll say that T and U are equiconsistent over B if T has a small consistency strength as U over B, and vice versa. So the strict ordering and the equiconsistency are defined exactly as you would guess from the original definition. So this is a way for comparing the relative strength of theories. The following results, as far as I know, are folklore. So the first theorem is that the consistency strength ordering is not prelinear, which is to say, there are non-equiconsistent theories, T and U, such that T is not strictly below U and U is not strictly below T. So these theories they're not equiconsistent, they're not comparable to each other. They're just incomparable. So when I say the consistency strength ordering is not prelinear, I mean that the induced ordering on the quotient structure modulo equiconsistency is not linear. The second theorem is that the consistency strength ordering is ill-founded, which is to say there's a sequence of theories, T0, T1, T2, and so on, a descending sequence in the consistency strength ordering such that each element of the sequence is consistent. Now, the first theorem here says that it's not generally possible to compare reasonable theories by consistency strength. And the second says that it's not generally possible to rank reasonable theories according to consistency strength. However, all of the known instances, at least known to me, instances of nonlinearity and of ill-foundedness were discovered by applying relatively ad hoc logical techniques. That is, to exhibit incomparable theories, to exhibit descending chains you resort to, say, self-reference to define those theories. These are not theories that appear in the wild, as it were, in ordinary mathematical practice. So an observation that many people have made is that the restriction of the consistency strength ordering to the natural theories is a pre-well ordering. So I have here a snapshot of a bunch of theories from subsystems of arithmetic up through the reverse mathematical systems, and then even to extensions of set theory by large cardinal axioms. And they form a neat, roughly well-ordered hierarchy. So when I say it's a pre-well ordering, I mean that the induced ordering on the quotient structure modulo equiconsistency is a well ordering. The resulting structure is called the consistency strength hierarchy. So there's this contrast between theories in general and natural theories, theories that arise in practice. And explaining the contrast here is widely regarded as a major outstanding conceptual problem in mathematical logic. Now, I say that it's a conceptual problem because, of course, it's hard to see how to approach this problem in a purely mathematical way. The notion of a natural theory is, it's not a precisely defined mathematical notion. It's an informal notion. So it's not as though we have some conjecture that we simply don't know how to prove. It's not even clear what to conjecture. How do you state a result to the effect that the natural theories are well ordered? So I have here a quotation from a paper of Cy Friedman and Ratyan and Weierman, where they write the fact that natural theories, that is theories which have something like an idea to them, are almost always linearly ordered with regard to logical strength, has been called one of the great mysteries of the foundations of mathematics. You can find similar remarks in other places too. Now, before continuing, I want to just mention that there is an analogous phenomenon that occurs in recursion theory. The Turing degrees are not linearly ordered, and the Turing degrees are not well-founded. You can use ad hoc recursion theoretic techniques, such as the priority method, to exhibit the nonlinearity in the Turing degrees, to exhibit ill-foundedness in the Turing degrees. Nevertheless, many people have claimed that the Turing degrees that are produced through the application of these ad hoc methods are unnatural. And again, it seems many people have claimed that the natural Turing degrees are well ordered by Turing reducibility. So I've been, for example, in workshops where the speaker will say, start naming Turing degrees. And people name Turing degrees: 0, 0 jump, the finite jumps, a 0 to the omega, Kleene-Zo, 0 sharp, maybe a few others. And it just seems that all the degrees with names fall into this well-ordered hierarchy where the successor is given by the Turing jump. So the phenomenon looks very much analogous to the proof theoretic phenomenon. So I'm going to today discuss research that attempts to make a dent on the proof theoretic problem, and I'm attempting to develop frameworks wherein the problem can be addressed. The approaches that I'm going to discuss today draw on connections between reflection principles and ordinal analysis, and also draws very liberally from this analogy between the proof theoretic and recursion theoretic phenomena. And these two themes will come up a few times during the talk, and you'll see how they're interwoven. So that was all by way of introduction. In the next section, I'm going to discuss work on the consistency operator. Some of this work is joint work with Antonio Montalban. In the next section, I'll discuss work on other reflection principles, specifically pi11 reflection. And the work in part 3 is joint work with Fedor Pokomov. Then we will return to this recursion theoretic question, and I'll discuss some joint work on the hyperdegrees with Patrick Lutz. So that's the outline of today's talk. Okay, so this work on the consistency operator is inspired by certain work in recursion theory. One of the properties that many people have noted about natural Turing degrees is that their definitions seem to relativize to arbitrary Turing degrees. So to make this precise, I will say that a function f on the reals is degree invariant if whenever two reals a and b are Turing equivalent. This implies that the outputs f of a and f of b are also Turing equivalent. So a function is degree invariant just in case it is inducing a well-defined function on the Turing degrees. As far as the Turing degrees of its outputs are concerned, the function only cares about the Turing degrees of the inputs. Now, if you take some of the, as it were, some pathological constructions in recursion theory that we use to exhibit strange behavior, and you try relativizing them, you don't get anything degree invariant because the construction depends on specific properties of the input set. It doesn't depend merely on the Turing degree. Well, what are the degree invariant functions on the reals? Well, if you try to name some, you'll see that the constant functions are degree invariant, and the identity function is degree invariant. And also the functions you get by relativizing the definitions of those natural Turing degrees are degree invariant. So the jump operator, x goes to x jump, and the hyperjump operator, the sharp operator, these are all degree invariant. Now, these are not the only degree invariant functions on the reals. You can easily cook up other degree invariant functions on the reals. However, the other degree invariant functions seem always to be mere variations on these. They seem to be always they seem, you can cook up a function, let's say, which is strictly speaking different from the Turing jump, but which seems to be equivalent to the Turing jump in almost all cases. So Martin has actually proposed a classification of the degree invariant functions in terms of their behavior almost everywhere. The notion of almost everywhere here is a specifically recursion theoretic notion. So I'll just say a word about what that is. A Turing cone is any set that we get by taking a degree B and then closing upwards with respect to Turing reducibility. So it's the set of all A that are Turing above B. It's the set of all A that compute B. And under reasonable hypotheses, it makes sense to say that Turing cones are big sets, and sets that are disjoint from Turing cones are small sets. So the almost everywhere here means on a Turing cone. That is to say, two functions will agree almost everywhere if they agree on a Turing cone. That's what the almost everywhere here means. Now I'm going to give a rough and sort of informal statement of Martin's conjecture. I can be more detailed in question if people want, but I just want to get across the gist of the conjecture. The conjecture says that the only definable degree invariant functions up to almost everywhere equivalence are the constant functions, the identity function, and the iterates of the Turing jump. So this is a proposed classification of the degree invariant functions. It's an attempt to get at this phenomenon that the natural degrees are well ordered by studying the natural degrees obliquely, as it were, through the degree invariant functions that they engender. Martin's conjecture is open. It's one of the I guess most prominent open problems in recursion theory, but various special cases of the conjecture are known. So there are results due to Slayman and Steele, and recently due to Lutz and Siskind that I know of that verify, give partial results and verify special cases. So now we're going to switch to the proof theoretic side of the analogy. So we're going to fix a sound, effectively axiomatized base theory T that contains elementary arithmetic. So in the same language. So elementary arithmetic is a subsystem of arithmetic that proves the totality of exponentiation. And it has induction for formulas that are bounded in exponential terms. It's a weak, I mean, it's strong enough for the usual arithmetization of syntax, but you can, if you don't know EA, you can think PRA or I sigma 1 or PA, and all these results will go through.
Excuse me, James.
Yes.
Emil Jerbeck has a question in the chat book. He asked, what does definable mean here? So,
as I said, it was just informal. So usually Martin's conjecture is stated in the context of determinacy, axiom of determinacy, assuming appropriate large cardinal axioms. The axiom of determinacy is true in L of R. And so one way of interpreting the conjecture is that it's about the functions that are in L of R. So it's a very liberal notion of definability.
Why don't you more attractively formulate it for Borel functions?
I guess you can do that too. Yeah, there are local.
I think he actually at least included that in his discussion.
Yeah. But I think the full statement of the full conjecture is usually just stated under determinacy. But I can give a more precise formulation in the questions if people would like. So okay, so this is the setup, and we're going to focus on functions, recursive functions that are monotone. What I mean by this is these functions induce monotone functions or order-preserving functions on the Lindenbaum algebra of T. So we're going to think of these as functions on sentences. And if T proves that phi implies psi, then T proves that G of phi implies G of psi. That's what it means for the function G to be monotone in this context. The goal is to show that the function which maps phi to phi and con phi and its iterates into the effective transfinite are canonical among the monotone functions. So just as Martin's conjecture is an attempt to show that the iterates of the jump are canonical degree invariant functions, the goal is to show that the consistency operator and its iterates are canonical monotone functions. So I'm going to get out of the way some terminology and some notation, which will make it easier to state some of these results. So when T plus phi proves psi, I'm going to say that phi implies psi. So I've fixed T. I'm just going to say phi implies psi. Second, I'm going to say that phi strictly implies psi if one of the following holds. Now, there are really two cases here. So the first case is what you would think, which is that phi implies psi and psi does not imply phi. And the second case is if phi implies a contradiction. So if phi is inconsistent, we're just going to say that it strictly implies everything. The reason for doing that is that this just, of course, it's going to cover some corner cases and allow us to state some of these theorems without specifically adding a clause that addresses what happens when phi is inconsistent. So for the statements of most of these theorems, when I say strictly implies, you can think of the first thing. That'll usually be what is sort of intended to come across. So that's strict implication. And I'm going to write that brackets phi equals brackets psi if phi implies psi and psi implies phi. So this means phi and psi are T provably equivalent. That is, the brackets phi is going to denote the equivalence class of phi modulo T provable equivalence. Okay, so before stating the first theorem, let me give my definition of a cone. Now, sometimes people think of Lindenbaum algebras going, stronger theories going up, sometimes stronger theories going down. So I apologize to those of you who are going to need to reorient yourselves, but a cone, the way I'm setting it up, is any set of this form. We take a sentence psi, and then we just look at all the phi that imply it. So a cone is going to be all the sentences that are stronger than some sentence psi. It's a set of all phi such that phi implies psi. Now, by true, in what follows, I mean true according to the standard interpretation of the language of arithmetic, so true in the standard model. A true cone is just a cone that contains a true sentence. So these cones are the cones you get by taking a true sentence and then taking everything that implies it. That's what a true cone is. True cones, of course, are going to be non-trivial. They're going to have lots of stuff in them, not just, say, inconsistent stuff. So that's what a true cone is. Now, we are going to, now I'm going to state the first theorem. I'm going to state the theorem, and then I'm going to try to say it in a more informal way to illustrate what's going on. So let G be a recursive monotone function such that for every phi, G of phi is a pi1 sentence. So G is a recursive monotone functions that, like the consistency operator, is generating pi1 sentences. Then one of the following holds. So the first case says that there is a true cone C such that for all phi in C, phi implies G of phi. And the second case says that there is a true cone C such that for all phi in C, phi and G of phi implies con phi. So a little bit more informally, what this is saying is the following. It's saying that we let G be a function which is recursive, monotone, and producing pi1 sentences. Either on a true cone, G is as weak as the consistency operator, right? Phi implies G of phi. Or on a true cone, G is as strong as the either phi is as weak as the identity operator, or G is as strong as the consistency operator, right? So the first clause is giving us that G is as weak as the consistency operator, and the second clause is giving us that G is as strong as the consistency operator. So in particular, there's no function meeting these criteria, which is intermediate in strength. Any such function has to either be, on a true cone, as weak as the identity or as strong as the consistency. So what about the iterates of the consistency operator? Well, if we have an effective, a sufficiently nice elementary presentation prec of a well ordering, we can informally define the iterates of the consistency operator along that presentation as follows. So this is informal, but con to the 0 of phi will just return a tautology. Con to the alpha plus 1 of phi says that phi and con to the alpha of phi are jointly consistent. And con to the lambda of phi will say, for every alpha less than lambda, con to the alpha phi is consistent. Now, some of you have seen iterates of consistency wherein at limit stages, we take the union of everything we had before. So we get an infinitely axiomatized theory at limit stages. But we're looking at the Lindenbaum algebra of T. So we only want to look at sentences over T. So even at the limit stages, we want the thing we get to be finitely axiomatized. That's why we do things this way. Why is there an additional con in the limit case? Just so that this is looks like a sentence. Just so that you can see the alphas on the inside of the consistency predicate. So strictly speaking, we define the iterates of consistency in T using the fixed point lemma. So we say that, so I just have, I mean, basically you unravel this and it says what those informal clauses above give. So I won't go into the details on this. So, to describe what happens with the iterates of the consistency operator, I'm going to say what it means for cofinally many true sentences to belong to a set A. So we're going to say that cofinally many true sentences belong to A if for every true phi, there is a true psi, which implies phi, such that psi is in A. So cofinally often in the ultrafilter of true sentences, you are getting into A. And the theorem, given enough restrictions on the elementary presentation prec of a well ordering, is as follows. So let G be recursive and monotone. Suppose that for every phi, phi and con to the alpha of phi implies phi and G of phi, and that phi and G of phi strictly implies phi and con to the beta of phi for all beta less than alpha. Then for cofinally many true sentences phi, phi and G of phi is going to be provably equivalent to phi and con to the alpha of phi. So what this is saying is we suppose we have a recursive monotone function G such that G is everywhere bounded above by con to the alpha and everywhere strictly bounded below by con to the betas for beta less than alpha. So it's always in that interval. Then for cofinally many true sentences phi, G has to be equivalent to con to the alpha. Now, so this is different from the last theorem in a few respects. So in the first place, we just get cofinal coincidence. So we're not getting coincidence on a true cone, which is stronger. Rather, we're getting cofinal coincidence. On the other hand, the way this proof works, we don't have to make this insistence that G is always producing pi1 sentences. So that complexity restriction is dropped for this particular theorem. So what this theorem is saying is that a function recursive monotone function with a sufficiently constrained range has to coincide with the consistency operator at certain points. And we can actually get a theorem like this even if we liberalize the constraints on the range of G considerably. So that leads us to this theorem. So let G be recursive and monotone, such that for every phi, G of phi is a pi1 sentence. Suppose that for every phi, con to the alpha of phi implies G of phi. And that for every consistent phi, phi does not imply G of phi. Then for some beta less than or equal to alpha and some phi, phi and G of phi will be provably equivalent to phi and con to the beta of phi. And moreover, this will happen at a non-trivial point. So what this is saying is we suppose we have a recursive monotone function which is producing pi1 sentences, which is everywhere bounded above by con to the alpha and everywhere bounded below by the identity operator. So it can be a pretty wide range, but the claim is that it must at some point be equivalent to some iterate of the consistency operator, and at a non-trivially. So this shows that the iterates of the consistency operator in some sense are inevitable. You can't avoid them all. Okay, so that is the work on the consistency operator. So now I'm going to turn to the work on pi11 reflection. The point of inspiration here was another result in recursion theory. And this is a theorem of Steele's. So let P be an arithmetic subset of R squared. Then there's no sequence A0, A1, A2, and so on, such that for each n, an plus 1 is the unique B, such that P holds of an and B. And moreover, an is Turing above the Turing jump of an plus 1. So what is this theorem saying? It's effectively saying that there's no arithmetic function producing a descending sequence in the Turing jump hierarchy. So if you look at the first clause, this is saying that P is, as we're acting like a function with respect to the elements of the sequence, right? So an plus 1 is the unique B such that P holds of an and B. And the second clause is saying that this is a descending sequence in the Turing jump hierarchy. An is above the jump of an plus 1. So this theorem you can think of as an approach to this question of why the Turing jump hierarchy seems to be well-founded with respect to natural degrees, insofar as it says there are no simple descending sequences. So that's one way of understanding this. It's saying there are no simple descending sequences in this hierarchy, simple in the sense of arithmetic. There's an alternative. So Steele's original proof is recursion theoretic. There's an alternative proof by Harvey Friedman, which uses the second incompleteness theorem to derive this result. And reflecting on the statement of Steele's theorem and reflecting on this alternative proof by Friedman were what inspired some of the results that I'm about to describe. And the thought was, perhaps we can show that there are no simple descending sequences in certain proof theoretic hierarchies in a similar manner. So we're gonna now, instead of working with EA, I'm gonna work for just a moment with B sigma 1. So this extends EA with sigma 1 collection. Again, I mean, this works for anything reasonable that's stronger than B sigma 1. So if you're not familiar with B sigma 1, you can think of another theory if you'd like. Oh, and recall that a theory T is sigma 2 sound. If for every sigma 2 phi, if T proves phi, then phi is a sigma 2 truth. So this sigma 2 soundness can be formalized with this sentence, RFN sigma 2 of T in B sigma 1. And the theorem is that there is no RE sequence, T0, T1, T2, and so on, of sigma 2 sound extensions of B sigma 1, such that for each n, Tn proves the sigma 2 soundness of Tn plus 1. So we have a certain proof theoretic hierarchy given by sigma 2 reflection. And there are no simple descending sequences through this hierarchy, simple in the sense of being RE, if the elements are sufficiently sound. So why focus on sigma 2 reflection? What about sigma 1 reflection? So sigma 1 reflection is the reflection principle, also formalizable in B sigma 1, that we get by considering the statement for every sigma 1 T provable, every sigma 1 T provable sentence is true sigma 1. And in the case of sigma 1 reflection, we actually do get descending sequences, simple descending sequences. So there is a recursive sequence, T0, T1, T2, and so on, of sigma 1 sound extensions of B sigma 1, such that for each n, Tn proves the sigma 1 soundness of the next. So something changes when you go from sigma 1 reflection to sigma 2 reflection. Well, we can get more robust results if we shift to a different, somewhat different context. So now we're going to move to the setting of subsystems of second order arithmetic. And our base theory is going to be ACA 0. So ACA 0 is probably familiar to most of you. It's a conservative extension of panarithmetic. It has arithmetic comprehension and set induction. Now, recall that a theory T is pi11 sound if all of its pi11 consequences are true. A pi11 soundness can again be formalized as a sentence RFN pi11 of T. This can be formalized in ACA 0. In fact, there are normal form results for pi11 for the complexity class pi11 that are available in ACA 0, but not in, say, RCA 0, which is a reason for focusing on ACA 0 as the base theory here. And we're going to focus on the following proof theoretic ordering. So we're going to say that T is less than U in the pi11 ordering if U proves the pi11 soundness of T. So this is similar to the consistency strength ordering. Now we're looking at pi11 reflection instead of consistency. And the theorem is that the restriction of this pi11 ordering to the pi11 sound extensions of ACA 0 is well-founded. So that is to say, there is no sequence, T0, T1, T2, and so on, of pi11 sound extensions of ACA 0, such that each proves the pi11 soundness of the next. So to be clear, this is genuine well-foundedness. It's not just a lack of, say, arithmetic descending sequences or recursive descending sequences or something like that. So we have this well-founded reflection ordering on the pi11 sound extensions of ACA 0. Hence, we can assign ranks, well-founded ranks to theories in this ordering. And those are what we call reflection ranks. So T sub RFN, this is the reflection rank of T. That's the rank of T in the pi11 soundness ordering, restricted to the pi11 sound extensions of ACA 0. So this metric measures, it gives us a way of ranking theories according to their logical strength for a certain notion of logical strength. What is the relationship between this notion and some of the classic proof theoretic notions of measuring the strength of theories? So recall that the classic notion here is the proof theoretic ordinal. So T sub WO, that's the proof theoretic ordinal of T. That's the supremum of the order types of the T provably well-founded primitive recursive linear orders. So this is a notion that I think many of you are familiar with. And I think it is often understood that when you calculate the proof theoretic ordinal of a theory, you have thereby, you've calculated its logical strength in some sense. You've come to understand its proof theoretic strength. So what is the relationship between these notions? Well, to state the connection, I'm going to just remind you, if you haven't seen it before, that ACA 0 plus is an extension of ACA 0 with the sentence that for every x, the omega-th jump of x exists. The omega-th turn jump. So ACA 0 says that for every set x, x jump exists. But ACA 0 is not powerful enough to form omega jumps in general. So ACA 0 plus is this extension of ACA 0 with this sentence. And the theorem is that for any pi11 sound extension T of ACA 0 plus, the reflection rank of T equals the proof theoretic ordinal of T, which is to say, there is a, as it were, a kind of cone of theories. So you take this particular theory, ACA 0 plus, and then everywhere above that theory, reflection ranks equal proof theoretic ordinals. So this result, I think, expresses in some sense that this conventional wisdom, it articulates in a particular way this conventional wisdom that to calculate the proof theoretic ordinal of a theory is to calculate its logical strength in some natural ordering. Okay, so that's what I wanted to say about pi11 reflection. So I'm going to start talking about work on the hyperdegrees, and I want to explain how I got there from this. So Steele proved that there are no simple descending sequences in the Turing jump ordering. That was the result that inspired this work. And so that led to this result that there are no simple descending sequences in the sigma 2 soundness ordering on the proof theory side. This in turn led to the result that there are no descending sequences in the pi11 reflection ordering. And so it seemed natural to me there should be some analogous result in recursion theory. If we move to a pi11 context in recursion theory, we should, so if we pick a suitable recursion theoretic degree structure and appropriate jump operator on it, we should get a wellfoundedness theorem. So the relevant degree structure is the hyperdegrees. So the hyperdegrees are a very well-studied recursion theoretic degree structure. So to reals have the same hyperdegree if they're equivalent. Each is hyperreducible to the other. So there are a number of different definitions of hyperreducibility. So we could say that A is hyperreducible to B if A is recursive in B to the alpha for some B recursive ordinal alpha. Alternatively, people sometimes give this other descriptive complexity definition. Sometimes it's stated as a theorem. And this is a degree structure, which comes with a jump. So if you relativize the definition of Kleene O to A, you get the hyperjump of A. And this is pi11 complete. The hyperjump acts like a jump. So for any A will be strictly height below its hyperjump. Now, to state the theorem, I want you to recall that omega 1A is the least ordinal such that there are no A recursive well orderings of the natural numbers. So you are familiar with omega 1 CK. So the Church-Kleene ordinal, omega 1 CK is the least ordinal such that there are no recursive. Sorry, omega 1 CK is the least. It's the least non-recursive ordinal, and so this is just a generalization of this notion. So omega 1A is the least non-A recursive ordinal. So this should say no A recursive well orderings of n of order type omega 1A. So so this is just a generalization of the Church-Kleene ordinal, and there's a theorem, a classic theorem due to Spectre, which says that if the hyperjump of A is height below B, then the omega 1 of A is strictly below the omega 1 of B. And there's a corollary of this theorem. The immediate corollary is that there is no sequence A0, A1, A2, and so on of reals such that for each n, AN is hype above the hyperjump of AN plus 1. So again, this corollary is a wellfoundedness result of the kind that we were looking for. It gives us genuine wellfoundedness, so no descending sequences at all through the hyperjump hierarchy. And the proof of the corollary is pretty much immediate from Spectre's theorem. If there were a descending sequence of this kind, such that AN was height above the hyperjump of AN plus 1, then we would have a descending sequence, strictly descending sequence in the ordinals. Omega 1 of A0 would be greater than omega 1 of A1, would be greater than omega 1 of A2, and so on. But the ordinals are well-founded, so that can't happen. So, okay, we have this recursion theoretic demonstration of this corollary. But what we did was to develop an alternative proof of this corollary. So the alternative proof doesn't mention admissible ordinals at all. It doesn't mention omega 1s. It's inspired by the Friedman proof that I mentioned before of Steele's theorem. So this proof of the corollary that I'm going to describe is a proof that uses the second incompleteness theorem in place of the admissible ordinals. So the fact that I want to record before sketching the idea of the proof is that ACA0 proves that for every x, the hyperjump of x exists if and only if there's a beta model of ACA0 containing x. So provably in ACA0, if you have a hyperjump of x, you have the hyperjump of x, then you can form a beta model containing x and vice versa. Okay, so how do we prove this corollary? So we want to work in the theory we're going to work inside the theory ACA 0 plus ds, ds for descending sequence. And ds says that there's a descending sequence of exactly the type we're trying to rule out. So ds says that there is an x, so a real encoding a sequence. For every n, xn is hype above the hyperjump of xn plus 1. So ds says there's a descending sequence in this hyperjump hierarchy. What we want to do is show that ACA 0 plus ds is inconsistent. If that's the case, right, then ds must be false because it will be refutable in ACA 0. So we're working inside ACA 0 plus ds. We're going to let A be our witness to ds. Right, ds is an existential statement, so let A be the descending sequence. A0 is hype above the hyperjump of A1. So we have the hyperjump of A1. The hyperjump of A1 exists. And then by the fact, we can construct a beta model, M, of ACA 0 that contains A1. Now, because of the closure properties of this beta model, it will also contain A2, A3, A4, and so on. So it looks as though it's a model of ACA 0 plus ds. It has all the elements of a descending sequence. Well, you have to verify that this is a model of ds, and it's actually not obvious from what I've said that it is a model of ds. Just because all the elements of the sequence are there, it doesn't mean that the sequence will be encoded in the model. So the bulk of the proof is devoted to showing that there is a tail of this sequence of sufficiently low complexity that it gets encoded in the model. And you can do this. This yields a proof of the consistency of ACA 0 plus ds inside ACA 0 plus ds. And then by the second incompleteness theorem, we infer that ACA 0 refutes ds. So that's the idea of the proof. Now, some of you heard so those of you in the right time zone heard some of us discussing this yesterday or a few days ago. So you get this, we get this wellfoundedness result from second incompleteness theorem. There are also versions of the second incompleteness theorem for beta models that we can get out of this wellfoundedness result. So there's a nice circle of ideas here. So let's return to this well-founded relation. So we have this relation, O of A, the hyperjump of A is height below B, and we've seen that this is well-founded. So we can rank reals according to their ranks in this well-founded ordering. So let's call the rank of a real in this ordering its spectre rank. And it turns out that the spectre ranks of reals are actually familiar values from recursion theory on a cone, assuming appropriate large cardinal axioms. So in particular, for any x on the cone above 0 sharp, the spectre rank of x is just omega 1x. So the spectre rank of a real is just the least non-x recursive ordinal. And I mention this theorem because I think it helps to just to clarify the analogy between these proof theoretic and recursion theoretic phenomena in this context. So I have here the two sets of theorems listed side by side. So first, we have the well-foundedness results. There's no descending sequence, no sequence of pi11 sound extensions of ACA 0, such that each proves pi11 soundness of the next. On the recursion theory side, there's no sequence of reals such that each is hype above the hyperjump of the next. And then in both cases, we find that on a cone, the ranks in these orderings are familiar values from the discipline. So for any pi11 sound extension T of ACA 0 plus, the reflection rank of T is the proof theoretic ordinal of T. And on the recursion theory side, for any X on the cone above 0 sharp, the spectre rank of X is the omega 1 of X. So these results, I hope, clarify to some extent this an analogy between these two phenomena. And I will stop there.